I'm excited to have you guys here in class. Okay, this week we're going to talk about roadway plans and profiles. The lab this week, we're going to start actually laying out a roadway out in the front yard. This one's going to probably take a couple weeks, but we're going to at least get started on it this week is the plan. That's not too terribly big. What we will have is a roadway. I don't recall off the top of my head. Say it's 24 feet wide, a standard like subdivision roadway, and we'll stake out 3 foot offset back a curb, and we will grade those offsets to a top of curb elevation. That's going to be the plan. And again, this will take a couple weeks to do. After that, we get that done. We'll also talk about intersections and the return radiuses where we have intersecting roads coming in, staking that out. But for now, let's dig into the fun world of roadway plans and profiles. So we're going to talk about this week, alignment concepts, reading plans, coordinates, horizontal curves, and vertical curves. Um, Again, I don't have this slide deck completely put together. We will probably stop at horizontal curves. We have talked about vertical curves here in this class already, right? Beginning of the semester, a little bit, maybe calculated one by hand. Yeah. We'll probably talk a little bit more about those as far as the plans are concerned, looking at them from the plans, um, but not really getting into in depth with them. Vertical. Yeah, honestly, in my whole entire life, I have laid out lots of subdivisions, lots of roadways, and have never in my life had to hand calculate a vertical curve other than here in school. Um, yes. And I started surveying like, I don't remember exactly, either the fall of 1996 or spring of 1997 full time, and went until surveying until February of 2025. So, in all that time, I never calculated a vertical curve. We looked at profiles, and when we had to stake out roadways, looking at the profiles, all the curb elevations, vertical curve elevations, were provided in the vertical curve itself. Or we had enough information in a data collector, the vertical curve actually, vertical profile put into the data collector where we could just have it calculated for us. What is construction layout for roadway locations? Layout is used to provide line, grade, has cross sections. The field application is translating design plans into physical points on the ground. I'm going to need to get a better, more readable view here, but the plan view is uh, looking, say, from like an airplane, if you were flying over looking straight down. That is the plan view. That is horizontal. So meaning all of your angles and distances are horizontal angles, horizontal distances. That is the line, the horizontal plane. Things are then referenced from this in station offset or coordinates, your northings and eastings. We'll talk a little bit more later in this slideshow about station offsets and coordinates. The main information when you look at these plan views, it's kind of hard to see with this little diagram here, but the red line is representing the center line of a roadway. Everything then is usually referenced off of that center line. That would be the center line alignment that we call it the center line alignment. Everything's will be referenced off of that. Excuse me. We will also have a profile view, which is on the vertical plane. So imagine taking that aerial view, slicing down through it, flipping it up on its side. We're looking at the vertical portion of it. It is a graph relating the centerline station and elevation data. So with this, we have two axes. Think of a graph paper, your x-axis and y-axis. Along the x-axis here, we have the stationing, the distances along the alignment. The vertical axis, the y-axis, is representative of elevation. These are typically exaggerated as well. So they're not a one-to-one scale. Usually they're two different scales, horizontally and vertically. This is where you would see the center line information, providing the station elevation, the grade, and the slope. So in this example here, if you can kind of see, the green line would be representative of the existing conditions, the existing ground where the proposed center line of the alignment is going to go. The purple line would be representative of the proposed alignment, the proposed roadway. And in the middle here, doing a transition from one slope to another slope, right here in the middle, we have a vertical curve, which we have talked about a bit in the beginning of the semester. I kind of feel like it's a little bit of putting the cart before the horse there, but due to the beginning of the semester and all the cold and snow that we had, I kind of had to transition things and make it math heavy in the beginning because we couldn't really go outside and do stuff.
We had a telephone company. They set poles like between our house and the neighbor. Well, they went down their neighbor's property line and our property line, and they cut across the field to this house that was being built. And they thought, the guy on site thought that the right of way went from the edge of the pavement over instead of the center line. He didn't read the plans.
Yeah, typically the right of way comes off of the center line of the roadway, or you can have, in the case of like you're talking about power poles cutting across a farm field or something like that, the center of the alignment would be the power poles themselves for like an electric line or whatever. And your right of way would typically be labeled off of that.
It's like 25 or 30 foot, what it was. But yeah, they measured 30 foot on the
Oh.
pavement when it should have been 15.
Uh,
So they were all like out in the middle of everybody's yard.
oh, goodness.
So that, yeah.
I bet that was a stink to try to resolve and get easements and things figured out or something.
Dad went up and said, hey, here's the rate plans. I don't know if you have rate plans or what, but handed them to them, and they're like, oh shit.
Yeah.
We were like, you don't have to pull them up, fine, but just because they still had to go down the road, it's like,
Maybe
set them in the right spot, and they went up anyways, whoever told them we didn't
put it in the right spot right away. Yeah. Yeah, you might be okay with where it was. However, when, yeah, neighbor's not going to be, or when you guys sell, the next owner might not be. You never know. Another vertical plane we look at is the cross sections. So with the profile, you're looking at along the horizontal centerline alignment. The cross section would be a vertical plane that is perpendicular to that profile, the typical section. It is also relating your offsets, elevations, and slope data. What I have here is an example of like a roadway typical section. So this is the way this is going to be built. The road is going to be built On the far left, your beginning point here is typically the center line of the roadway or the center line of your alignment, showing you how wide the pavement is, where your curb is, how they want this graded basically out to the right of way. And then there's some kind of a slope going out past the right of way, either a cut or fill to meet existing. Sometimes you may see in typical sections as well, they come off so far, come down and back up for a drainage ditch. That's not too uncommon to see as well. As you can see, these are your horizontal distances and how the roadway is to be built accordingly and graded. Anybody got any questions on a typical section? So your cross sections here, this typical section, again, is perpendicular to the profile, which is the center line of the alignment. Questions? Concerns? Comments? So there's a lot of different coordinates, a lot of different ways coordinates are defined. Some classifications of coordinates. We'll start off at the top there. We have ground coordinates, we have geodetic coordinates, and we have plane coordinates. Your ground and your plane coordinates, there is a difference. Well, there's a difference with all of them. You will hear talking about state plane, ground, grid when you're dealing with GNSS systems. Geodetic coordinates also are your GNSS type things, your latitudes, longitudes. And then coordinate systems, we look at them in two-dimensional, three-dimensional, and hybrid. Your two-dimensional are what everybody's familiar with, your Cartesian coordinates. Think of your graph paper, you have an x-axis and a y-axis. However, as surveyors, we like to flop those and we go with northings and eastings. Northings would actually be the y-axis and your eastings would be the x-axis. We also have polar coordinates, which reference angles and distances. So from a known point, go a distance, go a direction and a distance, bearing and distance. In three-dimensional, we still have our Cartesian coordinate system, which would then be like your x, y, and adding a z component. Cylindrical, talking about cylinders, we then start kind of getting into the polar again. Spherical, very similar to your geodetics where you have latitude, longitude, and height. Hybrid systems, which you will mostly see with your plan and profile roadway plans, you're talking about station offset and an elevation. Just to remind everybody, your Cartesian coordinates, your x, y, z. In surveyor speak, this would be our easting, this is our northing, and z would be referencing elevation. We've all seen this quite a bit before in the past. We're generally familiar with this stuff, right? I'll tell you what, using coordinates and calculating from coordinates like the inversing like we did earlier, to me seems fairly simple. Pythagorean theorem, breaking down triangles using sine, cosine, tangent. I think of this and I have flashbacks to like learning this, in middle school, high school, and the slope intercept, y equals mx plus b and all that good fun stuff, or however that one went. I might have butchered that equation right now. That just to me sounds like very confusing. I think our survey math is a touch easier to get everything you need. So talking about your cylindrical coordinates would also be very similar to your polar coordinates. Off of your x-axis, you have an angle, your distance, a radius, and then we can introduce our z, like our elevation, so the height of the cylinder. Does that all kind of make sense? Fairly similar there. Getting into spherical, now we're starting to deal with a couple different things. So maybe my lack of knowledge is supposed to be theta sub 1, theta sub 2. I don't know how to get the sub 1 and sub 2 symbols in there correctly, so that's kind of bad on me. Your radius from your origin point out to where you're going. Your theta sub 1 would be your angle referenced off of the x-axis here, and then your theta sub 2 would be the angle from your xy plane going up. So this is also like your geodetic coordinate systems, where we deal with latitude, longitude, and height.
So a radius and then the radius of each of the curves?
A radius and angles.
In my head, it's a little mixed up because you can also use like angles, I think. Or no, you can't use angles. I don't know. The AutoCAD and how AutoCAD writes things like that is messing with how I'm understanding it.
Oh, good, good, good. I'm glad that we're stretching the old thinky muscles this morning. Yeah, it.
Okay.
So this first angle right here is on the horizontal plane, the XY flat plane.
Right.
Okay, coming off of the x-axis
Right.
to some location where this is. This arrow here is coming off of that flat plane going up. So what is that measuring up from my origin point? If this is the ground, what's my angle that I'm measuring?
Are those given angles on a sphere, or are you just
Can
picking
be.
two spots on a sphere to be like angle here, angle here?
Well,
radius?
this is how latitudes and longitudes are derived from our geodetic datums. Our center point being like the center of mass of Earth.
Right.
Our x-axis would be the equator. Our y-axis would be going to the pole. So yeah, we're measuring from and our x-axis is along the equator. Well, where's 0 on that? Well, that would be where the Greenwich meridian would be. We're saying 0, and then we measure our angles off of that, east and west. Okay.
Okay.
Now think of this angle. Think of this angle going up from your equator, going up latitude lines, going up your latitudes. So you're measuring from 0 being the equator. You're going up. That's your latitude.
Right. Gotcha. That makes more sense. In my head, I was forgetting that we were measuring points on a sphere. I wasn't realizing the point of it is that it could be anywhere.
And
Trying to find out where on the sphere something is. I realized that I was trying to measure for the wrong thing.
yeah, this is a little confusing, kind of hard to think of. I guess to think of it in surveyor speak. We talk about our geodetic datums. We have an ellipsoid, which is a smooth, perfect mathematical model of the shape of the Earth. Okay. The origin point being the center of mass of the Earth. Think of your x-axis as going from the center of mass out to the equator. So there's the Greenwich longitude meridian line. That's 0. So we point towards that and we measure east and west off of that line. And then from your equator going up or down to the poles, you're measuring, latitudes. So this second theta here would be basically measuring up to whatever latitude you're going to. Your first one there, bless you, from your Greenwich meridian, you're basically going to be measuring longitudes. How far over from 0 are you going? It's the first time in my life I ever heard that sneeze. And think of the radius as from the center of mass. What's the radius of the Earth? But we have that ellipsoid, which is an oblate sphere, meaning that it is squished at the poles and fatter at the equator. There's a flattening factor and all kinds of fun stuff involved in that. But I don't know if that kind of helps visualize spherical coordinates.
It does. Well, I don't know. I
Right.
Are you just picking X? Why, like the XY plane goes in the middle of it. So that's the X plane. But what about the Y plane? How are you getting, I guess, theta 2 there?
The equator. So
Or I guess
you're
theta
standing
1.
at center of
Or I guess
mass.
theta 1 to X. How do you decide where 0 is?
That's the Greenwich meridian,
Okay.
which runs through Greenwich, England.
Do you have one of those for a sphere, or do you have to just make up the Greenwich meridian like we did, I guess?
I would assume if you're doing this in a trigonometry class, that's probably the origin's going to be given to you.
Okay.
Surveyor speak, Greenwich would be our 0.
Okay.
Always. So our latitude and longitude for like this location here, we are, I want to say somewhere in the neighborhood of like 84 degrees west. That would be as if we're standing at the center of the Earth, looking towards the straight out at the equator. 0 would be where that Greenwich line, meridian, which would be a longitudinal line, that we're saying that's 0. And we're going 84 degrees to the west from there, and that's where we are here in this spot. Then from standing there, the equator is 0. We're at latitude, I'm drawing a blank, something.
Right. It makes sense now. The Greenwich thing was what was tripping me up because I knew.
Where's your origin point?
Right.
Sure.
I knew in my head we have one of those in real life, but
Right.
you can't just pick one on a sphere, can you?
I
I guess you can. Thank you. Very informative.
it is a tricky concept to think of, and we will not really do any true hand calcs of this nature, but yeah, a longitudinal angle, a latitudinal angle, and essentially the radius of the Earth or of the from the ellipsoid, and there's a flattening. So that would be looked at as a height in geodetic speak. Lat, long, and height. Spherical coordinate. Maybe I need to get a better graphic to help represent that one too. That help?
Maybe. I don't know. I just feel like the issue was a lot of I just couldn't conceptualize that. I knew.
Where's 0?
I knew logically the Greenwich line exists. I didn't know the name for it. I learned
Yeah.
about that in like grade school.
Okay.
And we watched the video. There's a big line going through a museum. But
Yeah.
I could not for the life of me remember the name.
Yeah. Fun fact, that's probably going to change a touch.
I can imagine that. I feel like we're probably, I don't know. I feel like now would be the time a lot of surveying stuff and like general stuff changes. We're on the precipice of having to convert everything to digital.
Well, the fact of the matter, well, what we have, and this is from a geodetic standpoint here, we have an ellipsoid defined. Again, mathematical, smooth, perfect shape, rough shape of the Earth. This is what we use to establish our latitudes, longitudes, and elevations. For what we use here in North America, that ellipsoid is essentially best fixed to the North American continent tectonic plate, if you will. So our coordinates essentially are moving with that tectonic plate, and they don't move. They do, but they don't. What we have and where we're using that ellipsoid right now, from all the math and measurements that have been done, they believe that is about 2.2, 2.4 meters from what they believe to be the actual center of mass of the Earth. We are actually getting ready to modernize our datums where that ellipsoid is going to shift by a couple meters to the actual center. This is all a lot to do with the GNSS, the satellites and things. Those things are going around the Earth. The Earth is moving. So with this ellipsoid moving to the center of mass, this is going to take into consideration the tectonic plate movement of the Earth. So every couple years, we're going to have to update our coordinates because plates obviously move, shift.
What happens to like all old deeds, information that have like
37 degrees, if they reset that and move that over like 37 degrees, it's going to be the same spot, right?
Well, the thing is, you walk up to that monument in the ground, and it's there. It is. That's not changing. The actual coordinate value that we're placing on that monument that's right there in the ground will change. So what's really important moving forward when we start publishing our coordinates, our latitudes, longitudes, and things, we need to add a new component to our coordinates. You know, right now we basically do, I'll say, a northing easting elevation or a latitude, longitude, and height. We are now going to have to add a fourth component to that, which is going to be time, meaning when was this observed? So when you do go back to look at legacy data, legacy information, this was originally 37 degrees. How was that derived? What was that derived from?
Pre and post reset or recalibration or whatever.
Yeah, so we come here today and we actually hit 37 degrees 30 minutes by our new adjusted datums. This was originally 37 degrees or something like that, but that was derived from the legacy. So we're going to need to be aware of the time component, and that's kicking me down a rabbit hole here in another class that we get into that a lot more. But yeah, so the time is going to be critical, so we know this was 37 degrees at this time using this specific datum. Now we are here at this time with this datum, and now we're saying that it's now going to be this. That spot didn't actually move. It's still there. The coordinate values we place on it are going to change every few years now, moving forward. This modernization is going to be happening. It started actually years ago, and this datum is going to be dated 1922 or 2022. We're actually going to finally get that implemented maybe here in 2026 or 2027. Our datums that we've been using now are horizontal datum was dated 1988. It probably wasn't implemented and actually started to get used regularly until 90, 91. I'm not 100% sure, but it was a couple years after that time. Spherical coordinates. So what we'll typically see with roadway plans are your hybrid coordinate system, where we're talking about station, offset, and elevation. Stationing is going to begin at the beginning of the alignment and increase as you go along the alignment. So you will have a station along the alignment. How far of an offset do you have to that alignment? And then what is the elevation? So kind of still like an XYZ, just we're going to name it something a little bit different. Stationing is horizontal distances that are measured along the alignment. So for example, you will see a station maybe something like 0 plus 34.65. That means that is 34.65 feet from the beginning point, the beginning of the alignment. Or 19 plus 74.07 is really 1,974.07 feet from the beginning point on your alignment. Full stations are every 100 feet, half station 50, and a quarter station 25 feet. You may see delta stations, which would be the difference between the stations, also the distance along that alignment between the stations. So for an example here, I have what's the distance between station 6 plus 97.32 to station 14 plus 87.23. You're just going to subtract. What's the difference between those stations? It's just going to be a simple subtraction. And then your distance between those two along the alignment would be 789.91 feet. Yeah. One of these days, I'm actually going to do a little bit of research on where did the plus sign come into play. I honestly, to this day, still do not know exactly. I would kind of make an assumption because they wanted to label distances along alignments that maybe putting that plus sign in the middle there just kind of would break it up a little bit, saying, hey, this is the distance along your alignment. So you can kind of differentiate what your distances you're looking at, would be my guess. So it didn't get too confusing, like what's this distance? What's this distance? I got distances over here, I got distances along here. That would be my guess, but I honestly don't know what is the reasoning, where did those originate from?
It's because the tape was 100 foot long,
Okay.
and it's just to break up chain link.
Okay, so where did
the chain was 100 foot long?
chain was 66 feet long?
Um,
At least the Gunter's chain was 66 feet long.
tape, sorry, this is AI.
So where did the plus sign come into play?
Station is
Yeah, sure, well, that makes sense. If we're using a 100-foot steel tape, okay, station's 100-foot long steel tape. I can buy that. So I guess I want to specify here, or at least kind of point out, your first digit to the left of your plus sign is in the hundreds of feet. So if I took away this 1 and it was 9 plus 74, that would be 974 feet.
Yeah, it's just like 19 tape lengths plus 74 feet.
Okay.
That's, I guess that's, I don't know exactly why, but Google says.
I'm not going to confirm or deny the Google machine there, but I would like to know a little bit more deeper research as far as sources on that one. The Google machine may be correct, but I would like to just verify the sources on that.
I don't know. Gemini is one of those ones that I mean, this was before Chuck Norris died. It told me that Chuck Norris was dead like a year ago. Just it'll lie. I don't know why.
I don't know.
A problem with the GPT models too. The O2 lied about 12% of the time, and the O4 Mini lies about 66% of the time.
I've always been one of those people who always kind of question like the source information. Like one of the big things that I don't know, I kind of find it a little pet peeve of mine is when somebody starts off the sentence with, well, you know, they say blah, 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 blah. Who's they? For some reason, that makes people upset when I ask that question. Like, oh, I never hear nothing but good stuff about this product from their commercials. Okay, sure. What's the source of your information? I do tend to question, like, I don't just blindly accept, you know, they say.
We weren't
That was
witnesses or anything, but she took their like they have like a witness rule where if enough people see something happen, it happened.
okay.
Sort of took that where it's like in order to say something's true, you need at least 3 sources and 1 conflicting.
Okay. That sounds pretty legitimate. I like that. I like that. To believe something to be true, you need at least 3 sources and 1 conflicting. I like that. I like that.
She's my mom. She likes your have a great day on purpose. I told her
Excellent.
that. She thought it was really nice. It made her smile.
Good, good, good. I like to make people smile.
You do a good job at it.
So, yeah, we'll have to dig in deeper sometime, do a little bit of a deeper dive on the whole where did plus sign come into play. I honestly don't know. And again, the Google machine may be right, but I would still kind of like to verify those sources that it comes from. Especially, yeah, if it comes from AI, I really want to know. What sources? I don't know. You said something like, "Hey, I told you Chuck Norris died last year." Right? Well, I actually heard Chuck Norris died like 20 years ago. Just death actually finally got the courage to go up and tell him.
Yeah.
I love those Chuck Norris jokes. They're funny.
I do too. I always love those on the playground. He doesn't do push-ups. He just moves the world.
Yeah. Good fun stuff. So aside with stationing, we also talk about the offsets. That is going to be the horizontal distance left or right of the alignment. Those labeled on the plans will be designated if it is left as a negative distance and to the right would be a positive distance. Offsets are measured perpendicular to tangent lines and measured radial to a curve. Make sense? And talking about elevations, your vertical distance is above or below the vertical datum. Above the vertical datum will be labeled as positive, and below the vertical datum will be listed as negative. Does that make sense? Does this help with that? A graphic of this here. So your offset perpendicular to your alignment within the tangents. If the stationing is going from left to right in this example, your particular structure or point is to the left, that would be labeled as having a negative offset, perpendicular in the tangents. You have a horizontal curve, this point here being on the inside, being to the right, would be labeled with a positive offset, and it's going to be radial. Does everybody understand what radial means?
Because it's a curve, it's radial.
Well, yeah, because of the curve, it's radial. Now, if you took your two lines and intersected and found your radius point, you go from your radius point through your point, extend it to the actual alignment itself. That would be a radial line. Radial lines go to the origin or radius point of a curve. So even if you had a point out here, your offset would be radial. That would be taking that line, projecting it straight to the radius point. That would be your offset distance. Perpendicular lines, radial lines make math a lot easier. We like this sort of things, especially if you're doing the math calculations by hand. Good geometry. So does that kind of help visualize, maybe make a little more sense as far as the offsets? If it's to the left of the alignment, it's going to be labeled as a negative offset. To the right, it would be labeled as a positive offset.
Is the one on the right supposed to have a plus on it?
Yeah, there is. There's a little plus up there.
Oh, like the one in the middle is plus, but not the ones on the sides.
These two?
Yeah, those two are meant to be.
Yes. So here we have a little label that says stations with an arrow going this way. So our stationing is increasing as we go from the left to the right. That's also very critical to determine which way your offsets are left or right, is which way is the stationing increasing. If, for example, the stationing was actually increasing from the right to the left, this would be labeled as a positive offset. This would be negative if the stationing was increasing going this way. The direction of the stationing is critical to determine which direction your offsets are going. Yeah, what?
It's like the buttons on a Wii remote.
Sure.
The pause and the select and start are minus and plus, and they're only on the left and right if it's facing the right way.
Okay, yeah.
I mean, that's a weird way to think of it.
Yeah. I'm not a gamer. I don't really know what the world you're talking about, but I'll say yes, that sounds good. It's plus or minus as long as you got it oriented in the right position.
Right.
Yes, I can understand that concept. That is correct. I think analogies are a good thing. If you can kind of see, it's how does that saying go? It's easy to understand something when you can relate it to something you already do understand. So if you understand the Wii remote thing, now you can understand the stationing because you can apply that in a similar way. Yeah, good, good. Thanks for the input. I like it. So, conversion of hybrid coordinates. We can convert station offsets to northings and eastings or polar coordinates, polar being the angle distance, along alignment tangents and along alignment curves. We can convert northings and eastings or polar angle distances to stations and offsets along alignment tangents and along alignment curves. This is a very simple example here, and I hope this would kind of make some sense here. If we see the stationing here, 6 plus 0, 0, 15 plus 0, 0, or 15 plus 50, we can tell along this alignment, station is increasing as we go to the right. Yes? We also see 25-foot left, which would also be labeled as a negative offset, 25 or 50-foot off to the right. We have a coordinate down there at the far left side, and we have a bearing. We could easily calculate the polar coordinate to this point here. This right side here, station 0 plus 0, I'm sorry, left side 0 plus 0, 0. This is station 15 plus 50, so we know the length of this triangle. We know this is perpendicular, right triangle. We know the length of this side, right? The right triangle's coming back into play. So the polar coordinate would be an angle and distance from this point going straight over to this. So what would that angle up from the alignment be? And what's the distance? Well, we know two sides of our triangle, opposite over adjacent, that would give us the tangent, right? We know two sides, a squared, b squared, c squared. We could find essentially the hypotenuse of that. Right triangles, they're everywhere. Likewise, we have a station offset here, we have a station offset here. We could find the distance between those two, the angle in between those two. We know we would basically draw a full triangle, either come up and over or all the way down and over. This side of the triangle would be adding the two offsets. This side of the triangle would be subtracting your stations. You got your up and over, your latitude, your departure, your northing, easting, difference in your northings, difference in your eastings, however you want to say it. Be very simple then to calculate what's the distance between those. Back in my day, Sonny, before data collectors, when I had a survey uphill both ways in the snow and we liked it, stay off my lawn. After this, I got to go outside and yell at the clouds. Seriously, though, back in when I first started, when I was like your guys' age, when I first started getting into this surveying, we literally did have to hand calculate everything we had. So if this was like, say, a center line of a subdivision road, this is two manholes or something, or we had to stake out. We were given the center line alignment information. We would actually occupy on that center line, backside the other end of this tangent, and calculate how far up, how far over, and calculate what angle we had to turn in the distance we had to go to actually set that point. And then likewise for the other one. So seeing the triangles, knowing the triangles are, I think, very important. And again, when you go take your fundamentals exam, knowing the math will just keep that reinforced in your head. It will benefit you. Likewise, say if we were to convert back over to a polar, well, yeah, I guess we kind of already talked about that. We talked about the angle and distance. If you knew your angle and distance and needed to find these stations, if you already have that angle and distance, you got this angle, you got your hypotenuse, you'd need to find your adjacent and opposite sides. You could even break that triangle down, or your latitude and departure, however you want to call it. It's all the same math. In roadway plan views, there's two major features. You have your tangents and you have your curves. Your tangents are going to be your straight lines. You're going to have bearings, distances, bearings or azimuths, most likely bearings on all your plans. Curves, talking about horizontal, the easy to calculate kind. We have our simple circular curve. We have compound curves. We have reverse curves, and we have spiral curves. We've talked quite a bit and calculated simple curves earlier in the semester. Compound curves, as you can see, would be two simple curves exactly next to each other but have a different radius. And something that is very critical, these two are also what we would say radial to each other, being this end, you go to the radius point, this line is going to be the same for this curve where this part goes to its radius. That line's the same between those two. Very critical. Good geometry, good math. You can see compound curves more likely in subdivisions or on roadways where the speed is generally considered to be low. Your reverse curve would be where you have two curves, two simple curves again, put together, however, you're traveling in the opposite direction. And again, they should be radial to each other, meaning where this point of intersection, if you draw from this radius point, you will go pass through the point of intersection where they meet and transition from one direction to the other. Reverse curves, those can be the same radius, they can be different radiuses, radii. Again, you can see these on roads where your speeds are a lot smaller, lower. Spiral curves are typically used on the highways where speeds are a lot higher. You have two tangents. You can't really safely at a higher speed make this sharp of a turn. So we put a spiral curve, which is kind of more or less like a parabola. There's no defined radius point on either side to help make the transition into your circular curve, and then another spiral coming out and then going into your tangent. And you're going to see that on the highways, higher speed, just to make that transition smoother for vehicles going from one tangent direction to another. We've gone over and talked about horizontal curves. They're defined by 8 elements. Your central angle, also called like an interior angle, I always refer to it as a delta angle, usually represented by the symbol, Greek symbol delta. You have your radius, tangent length, arc length, long chord. The long chord is your distance. I also do reference bearing and distance. That is not uncommon to see a bearing and distance on your long chord. You have a degree of curve, you have a middle ordinate, and you have an external. The degree of curve is easier to use with calculating things. However, just the way I had done stuff growing up in the surveying world and hand calculating things, I never myself used degree of curve to calculate. It is also defined differently depending on whether you're talking about roadways or railroads, and how much angle is subtended by 100 feet of arc length would be a roadway. Your railroads are how much of an angle is subtended by 100 feet of chord length for railroads. I believe I got that correct. Didn't spin that around the wrong way. Parts of the horizontal curve, we'll go ahead and talk about this again. So from your radius point to your tangents, that distance is your radius. These lines should be perpendicular to the tangent in, tangent out. The angle between these two radius lines would be that interior angle, that delta angle. The arc length is the actual length along the curve, along the alignment. Your long chord would be the straight distance from the beginning of the curve to the end of the curve. We have the tangent length, which, if you project your forward tangent and back tangent to the intersect, that would be the distance from this point of intersection down to the beginning or the end. Tangents are also equal in lengths. You should not see a tangent of one length here and a different tangent length here. Same thing with your radius. Your radius should be the same on both sides. If things start getting different, you're not dealing with simple curves. Your middle ordinate would be the distance from your long chord to the actual alignment itself. And your external would be from your point of intersection down to the alignment or the center of the arc. Again, your degree of curve for roadways is how much angle is subtended by 100 feet of arc length for roadways. So some other little nomenclature I don't have on that other slide. We have this PC, point of curvature. That is the beginning where the tangent stops and the curve begins. PI, point of intersection, where you extend your forward and back tangents into each other. PT is your point of tangency, which would be where the curve ends and the tangent line begins. Bless you. Anybody got any questions on horizontal curves or the general nomenclature of what each part is?
How much do railroads differ from, I mean, just roadways, period?
When you're talking about the horizontal curve, so like your degree of curve here, so this is how much angle by 100 feet of arc length. That's the road different. That's the road. The railroad would be a chord distance there, and that's 100 feet. So that does change slightly depending on how tight your radius is. That's kind of probably the biggest difference as far as horizontal curves and railroads versus right-of-ways.
I feel like most railroads probably have a really, really long radius
Yeah,
where, you know,
I've not.
turns.
I've never laid out a railroad before in my life. I've looked at val maps and been more concerned with the railroad right-of-way.
We've had to deal with issues a lot with railroad stuff over in like southeast Ohio, where it all used to be coal.
Yeah.
And so all kinds of railroads going around there to get coal out, and it's just a mess. they'll abandon it, but the company will still own that land, and we'll just build driveways down it and stuff.
So when you start talking about road right of ways, railroad right of ways, there's a few different ways right of way can be taken. And you probably will get into this in other classes like boundary class and stuff like that, boundary law, where you have things that are taken in what's called fee simple. A right of way taken in fee simple. That basically means one entity purchases the land from another. So they own it, they're putting in their road, their railroad, whatever. There's also by easement. You can have a right of way by easement, which you might see a lot more out in your out in more rural areas where like everybody's property lines go to the center line of the road, but there's still a right of way. That's an easement. Typically, in that case, if the road gets abandoned, vacated, or something, that easement would expire. Meaning the people still own that land. However, there's a public access right of way that the public can still use that land while that is in use. If that ceases to be used for that reason, a lot of times that easement will extinguish and everything goes back to the way it used to be prior to that road. That can vary. Railroads are really odd in their own way, and they have their own rules. And I don't know. I heard once a long time ago, I believe this to be as a joke, the hierarchy of power in this country is you have the government level of power, you have the God level of power, and then the railroads are above that. Like the railroads can do whatever in heck they want, however they want. They do have a lot of authority and a lot of control, and they can be challenging at times to either gain access to their right of way or anything.
See that railroad land, the last thing they had, they still own the land, but they tore the railroad up, abandoned it.
Well, if they actually own that and that was bought in fee simple, meaning they purchase it, if that railroad's gone, they still own that land and that's still theirs.
We run into stuff a lot of times, people will just completely ignore it and build a driveway right through it.
Mm.
And then we have to wait for them to get an easement done either through the railroad company's land or the railroad company makes them buy the land, like a certain amount of it from them.
Oh yeah, yeah. Dealing with the railroads are very weird. I've never dealt with them directly, but I've worked on projects where even like Duke Energy, for example, power lines crossing railroads. You know, power lines are going whatever 50 feet over the railroad track. Yet for the utility company to get an easement going across the railroad track was quite an ordeal and process that other people in the office dealt with. But I was usually the one out in the field who was doing all the locating and things of what was where. And the railroad even requires the utility company, like, okay, you want to cross this, we'll let you. However, we're going to make you do steps 1, 2, 3, 4, 7 through 10, whatever. All these steps. We need to know all this information. It can be kind of crazy. It's interesting. The joys of surveying. Am I right? Hold on a second here. I want to. Let's go a couple of things here real quick. So kind of talking about horizontal curves and layout in regards to this. A lot of times what we will calculate and do would be calculating our long chords to various points along the alignment. So what I would mean is you have your instrument or something set up at your PC, backside your PI, calculate and turn angles, deflection angles through this, and calculate your distances from your PC to each point specifically. Long chords. When you talk about short chords, that is essentially just what is the distance between the points themselves specifically. So if you're setting out these points that are at every, whatever, 25-foot station, 50-foot station, these short chords between these even stations are going to be the same. Once you calculate one, you have the rest. Until you get close to like your PCs and PTs, you get something a little different. You'd need to calculate those individual. Deflection angle to any curved station is your half delta. I don't like the way this is written out because to me that just looks a little confusing. We've gone through a lot of this stuff already though. So again, from your radius line to your radius line, that full is your full delta. When you start looking at your long chord between your PC and some point, you have your arc length, you have your radius, you can calculate the interior angle for that portion. Once you do that, you have your half delta, you can calculate your chord length from there. Now, your deflection angle, once you have the delta for this particular portion, from your PC to your PI along that tangent, the angle, your deflection angle that you would turn there is also equal to the half delta. And that should probably ring a bell when you look at your actual chord when you're going from your PC to your PT. From this tangent to that chord is equal to the half delta of the whole entire curve. Did I say that clearly? It made sense in my head. I still got eyeballs, so I'm happy with that. I guess I'll go with that. Okay, that's the end of this little part here. Anybody got any questions on anything that I did not clearly explain? Oh, I like this. Let's look at this little guy here. Oh, which ends up on this? This looks confusing. Oh, I like that. Let's look at that one too. Oh, I like that one. Let's look at that. Maybe. Maybe that'll be more confusing. I don't know. So here to kind of also reiterate, I'll put my lecture slide on Brightspace, as well as some of these extra handouts here. Maybe this might help a little bit if you were looking at your XY coordinates or XY values, your XY grid. The plan view would be looking down, like an aerial view, looking down flat. Your profile view would be slicing that alignment and looking at it from a vertical standpoint. The cross-sectional view was also vertical like the profile, however, it's perpendicular to that profile view. Profile cross-section are vertical views perpendicular to each other. All right. I don't know. Does that kind of help clarify or help make sense, or another way to visualize this? Does that help, or does that look more confusing? Good. How about this one? Does this help confuse? So down here at the bottom, you have a plan view. Now we're going to cut that profile. Here's the profile view. And then I guess you got like basically an isometric showing the grading for the whole entire road compared to your existing.
Well, that's actually pretty helpful.
This particular line right here would be the existing ground. So where the road is above it would be fill. We have to fill in a bunch of dirt. Where the ground is, or the proposed road is below, would be where they have to do some cut. So in this particular area, I would say it's probably this stuff right in here showing fill down to wherever it ties into the existing at some designated slope. I don't know. Does that help, or is that confusing as well? Should I add this?
I think the isometric one, like crossing over onto the other graph, like when I first saw it, it was a little confusing, but now that they're all explained, that's not easier.
Here's a good example of the profile view straight on. So that is cut along the center line of the proposed road. This solid line up here, jagged line moving all over the place, would be the existing ground, existing conditions. Their dark solid line would be the proposed roadway. Obviously, where the proposed road is below the ground, existing ground would be cut. And up here, where the proposed road is going above the existing ground, would be fill. So as you see here too, we have our stationing. And it looks like stationing is actually going from right to the left, which is odd. Typically, I feel like I've always looked at it, it's always been going left to right. However, what you're seeing here down at the bottom, you'll see two sets of elevations at every, what was that, half station, every 50-foot station. The existing ground elevations are going to be shown to the nearest 10th of a foot, and your proposed roadway design elevations are going to be to the nearest 100th of a foot. Now, if we look here through this vertical curve, we got a 200-foot long vertical curve. As you see, when you're staking out roadways, you're typically going to lay out something like every 50 feet or 100 feet along the tangents. If you lay out 100 foot along the tangents, you would lay out like 50 feet along the curves. Or if you're laying every 50 feet out through the tangents, you're probably going to lay every 25 feet out through the curves. Either way, we're seeing at every 50-foot station here, we're seeing our elevations through here. There are proposed elevations. So that is why I've never actually had to do any hand calcs, because looking at profiles for roadways, that's information that had always been right there. When we look at our typical sections, we can calculate how high or low is the top of curb from the center line elevation. And we could do all of our math going out from there. How fun. There's a good looking straight at just the plan. So you see with your plan view here, we're starting down here at station 0, and we are increasing. We have a PC in a station, we have a PT in a station, we have curve information of our delta, radius, tangent, and arc length. If we need to calculate anything else, we have more than enough information to do so. A lot of times, especially on highway road plans, you'll have your beginning and end of curve stations, your PCs, PTs, and just a bearing along the tangent. You can easily take your PCs, PT stations, subtract the difference to get what is the length between those stations. Anybody have any questions on any of this so far? Does this kind of help or hurt or make sense? So here's your plan, here's your profile, put them both together. Here's your plan and profile together with an isometric view showing how everything works together. Does that help? Hurt? Make sense? I don't know if this is going to be a little extra confusing or not. So looking at your graph again from your origin point, your y-axis being your stationing, your x-axis being your offsets. So to find some point, how far off of the x-axis, how far along your station, how far off of the y-axis is your offset, and then your elevation would be basically your z. I guess that's kind of self-explanatory. Does that look like a clear representation? Kind of help make sense, or does that kind of seem a little extra muddy? Got one more thing we could take a look at quick here is an actual example of some ODOT right-of-way plans. There is gobs of information on here, and it can be very challenging to see what's where, especially when you have to take a set of these plans and manually input them and recreate this in CAD. We have the center line of the road. I believe there should be some bearing on there somewhere or another. A lot of stationing. But we have the plan view on top, the profile view on the bottom. Do we have a scale listed on here as well? Your horizontal scale looks like a 20. Typically, this should be listed here as well. Your x-axis, your stationing is going to be at one scale. Your y-axis, your elevation is usually a different scale. Again, it kind of exaggerates so you can kind of see the vertical component. Otherwise, a lot of these will look relatively flat, and it's kind of hard to see where all the vertical components are. So they do change the scale. These are a difference in elevations, 670, 675, 680. So you can kind of see where everything is roughly. There's a lot of information on here. Now we got center lines of construction. We've got center lines of the road. We got section lines in here. Whole mess of things. But wait, it gets better. Look at this mess of stuff. I'm not going to try to even pick all this out. I'm sure it's probably very difficult from where you're sitting to even make anything out here. Intersections of roadways. Talking about stationing. With curve data here, you do have your PI stations, your delta, a degree of curve, a radius, tangent, length, external, something else in there. Something really interesting to look at and pay attention to is if you see a degree of curve listed, this one's listed at 2 degrees, 0 minutes, 0 seconds. When you have a case like your degree of curve is an even angular value, your radius is going to come up to be something long, kind of weird, not to an even foot. In subdivision plans, you'll typically see radius listed to an even foot. Very common. But when you see, like, this was designed using a degree of curve, your radius is going to come out to like decimal feet. Any questions on anything so far? Good? Exciting? Yeah. Okay. Well, I think that's about all I have for today. Thank you for being here. I was just as excited as you guys to be here. Super excited. Thank you. Let's do it again.